Okay, so in class today, we looked at two cases of a car going around a curve, and we derived expressions for the maximum speed of a car going around an unbanked curve. That's a flat curve, but one that has friction on it. And then you did one that is a banked curve, kind of like in this picture right here, but with no friction. So now we're going to do a problem that has a banked curve, like this, but with friction. So we're kind of combining the two problems we did in class into one problem. So this is going to be a pretty heavily mathematical problem this time. So we're going to start with the free body diagram, as always. And on the free body diagram for this car, we have the downward gravitational force. We have the up an angle normal force, since it's on an incline. There is a frictional force, which on the flat curve, the frictional force was directed horizontally. But remember, the frictional force is always parallel to the surface. Normal force is always perpendicular. Frictional force is always parallel. So if the car is trying to go its maximum speed, that means it would slide outward. So the frictional force is going to be directed down the curve. So we need to have a frictional force going in this direction. And that's it as far as the forces go. There's no applied force, there's no tension force, and no drag force. So we have a situation where we're going to have to break some things into components. And in this case, it looks like it would be easier to rotate the axes, just based on the fact that the normal force and the frictional force line up with the rotated axes, and the gravitational force would have to be broken into components. But remember, you have to also take into account the centripetal acceleration. And if you look at how this car is going around the curve, the centripetal acceleration of the car is going to be directed toward the center of the circle. So it's going to be kind of going like in this direction, which is parallel to the actual ground down here, not parallel to the curve right here. So if I put that on the free body diagram, or near the free body diagram as the centripetal acceleration, now you can see that there's not really one good way to do it, because if I rotate the axes, then this and this are lined up, but the acceleration and the gravitational force are not lined up. And if I don't rotate the axes, then this and this are lined up, but these two aren't. So it's kind of 50-50 at this point. But the general rule is that you will find problems a little bit easier if you always line up the axes with the acceleration. It becomes a bit more complicated if we break the acceleration into components. So try whenever possible. If it could be the same either way, with rotating or not rotating the axes, try lining the axes up with the acceleration. So that being said, I'm going to draw a horizontal and vertical set of axes. And on that set of axes, if I label some things on here, this angle of the ramp is going to be the same as this angle right here, the angle between the frictional force and the x-axis. If I drew this free body diagram directly on top of this car, you would see that this and this are alternate interior angles. And then since these two lines are perpendicular to these two axes, that means this angle right here is going to be the same as this angle right here. So we'll go ahead and label that one between the Fn and the y-axis. We're going to label that as angle theta also. So now before I move on to solving part B, I want to redraw this free body diagram with everything broken into components. So I'm going to leave the FG on the negative y-axis. I'm going to break the FF into a component going this way. You can see that's going to be FF cosine of theta, and then it's going to have a downward component also, which is going to be FF sine theta. And then the Fn will also be broken into components. You can see that with the Fn, this upward component is going to be the one, since that's closest to the angle, the upward component is going to be the Fn cosine of theta, and the rightward component is going to be Fn sine theta. And then just as to remind me, I'm going to go ahead and put the centripetal force back on here in that direction. So now I can start looking at how to get the answer to part B. So let's focus on the horizontal motion first, because that's where it's accelerating. It's got centripetal acceleration in the x direction, so we're going to use Newton's second law in the x direction. So we'll say the net force in the x direction is mass times centripetal acceleration, and the net force in the x direction, we just have these two forces both pointing in the positive direction, and we have nothing over on this side in the negative direction. So I'm just going to add those two forces together. We have Fn sine of theta plus Ff cosine theta is equal to MAC. And let's go ahead and plug in some formulas. So we have a formula for the frictional force, and because you want the car to be able to drive as fast as possible, we can use the maximum static frictional force, and we also have a formula for the centripetal acceleration. So this will become Fn sine of theta plus mus Fn cosine theta is equal to mv squared over r. And we can factor an Fn out of these two terms right here. We cannot cancel that altogether because there's no Fn in this term, but we can at least factor it out here. So that's going to leave us with Fn times sine of theta plus mus cosine theta. And if you look at that stuff in parentheses, you'll notice that that is the numerator of the expression we're trying to solve for that's under the square root sign. So that kind of gives us an idea that we're on the right track. Remember, this is equal to mv squared over r. That's about as far as we can go on that side. So let's now look at the y direction forces. So we have a vertical force pointing upward, and we have two vertical forces pointing downward. And because there's no acceleration in the vertical direction, that means we can use Newton's first law. The net force in the y direction is equal to 0. We use Newton's second law for the x direction because there's acceleration in the x direction. We use Newton's first law for the y direction since the car is not accelerating vertically. So in the y direction, that simply means we can just say the upward force is equal to downward forces. So we're going to write that by saying Fn cosine of theta, the upward force, equals, and let's add those two downward forces together, Ff sine theta plus Fg. And let's go plug some formulas in. So we have Fn cosine theta, nothing changes about that one, is equal to mus Fn sine theta plus mg. And if we want to solve for the maximum speed that the car can have, which is back over here, all of this stuff is going to be valid, but we need to come up with something for Fn to plug in. So we can get the Fn from this equation right here. Notice it's in two places, right here and right here. So we're going to move this term over to this side of the equation by subtracting it, and then factor out the Fn, and then we're going to have Fn equals to, we'll have Fn is equal to something that we can then plug in over here. So let's do a couple steps at once. Let's subtract this term from both sides, and at the same time, factor out the Fn. So we have Fn, and then the cosine theta from this part right here, and then with this term being subtracted, with the Fn factored out, I'm left with a minus mus sine theta. So minus mus sine theta, and that's equal to mg. g, which means that Fn will just be equal to mg divided by all this stuff in parentheses. And I'm not going to rewrite it. I'll just put an arrow pointing down there. So now that we have the Fn, let's take that and plug it in to that Fn right there. So we have mg over all of this stuff, which we move down here. So that is over cosine of theta minus mu s sine theta times all this stuff, which goes in the numerator, and that's going to have to be in parentheses, is equal to mv squared over r, and, well, I think I've already probably done more than I need to. You can figure out the rest of this based on what cancels out on both sides, and then just solving for v, and you've already got the final answer given. So, let's jump down to part C, which just says, derive an inequality statement for mu s that must be true in order for the expression to be physically meaningful, and the hint that's given is what must be true about that denominator. So, for a denominator of a fraction, you know, there's one thing that always has to be true about a denominator, and that is that the denominator cannot equal to 0. You can't divide things by 0. So first thing is the denominator can't be 0, but the second thing is, when you're solving for this v squared back in part B, or the v, because v is squared, you would have to take the square root of this entire expression. And so, you cannot have the square root of a negative number and get a real answer, which means that in the denominator, since we have two terms that are being subtracted, that cannot be negative, which means that not only can cosine of theta not be equal to mu sine of theta, because that would make it 0, but at the same time, cosine of theta must also be bigger than mu sine of theta. I guess to technically not be negative would say greater than or equal to, but since we've already said that it cannot be equal to, all that we can say now is that the cosine of theta has to be greater than mu sine of theta. So we'll say this over here. The cosine of theta has to be greater than mu s sine theta. That would prevent the denominator from equaling 0 as part of the fraction, and it would also prevent the square root of the whole thing from being negative. So let's simplify this expression for mu s. We're going to divide both sides of the equation by sine of theta. So the sine of thetas cancel out, and now we have mu s by itself. So I can write that as mu s. Since I'm switching the sides, I'm going to switch the order of the sign. Mu s is less than, and cosine of theta over sine of theta, if you've gone far enough in trigonometry, you know that that's equal to the cotangent of theta. So that's an expression that must be true in order for this whole derivation we just did to actually have physical meaning to it.